Hello, I am Faizan Mujawar from Department of Aeronautical Engineering ADCT Ashta. In this video, we'll see about the recent developments in non-destructive testing for aerospace composites. So let's take a look on the content of this presentation. First, we'll see what is NDT and definition, then objective of NDT test, types of NDT, and what are the common defects which can be identified by using NDT test. So applications and challenges which will be faced during NDT test, and recent developments in NDT introduction, flash infrared thermography, large area ultrasonics, and computational ND. And at last, we'll see conclusion. Let's start with definition. So, non-destructive testing is the testing of material to detect the internal and surface defects or discontinuities using the method which do not damage or destroy the material under test. So, there are some objectives for the NDT test to avoid the failures, prevent the accidents, and save the human lives, and to make a profit for the user and to aid in the better product design. Also, to control the manufacturing processes and to lower the manufacturing costs, to maintain uniform quality level and to ensure the operational readiness. So there are some methods and types of non-destructive testing, in that visual inspection, liquid penetrant method, ultrasonic inspection, radiography method, ED current testing, magnetic particle testing, acoustic emission testing, fluorescent penetrant testing, and thermography. So what are the common defects which can be identified using non-destructive testing? So as you can see in this figure, these are the defects which can be easily identified using the non-destructive testing. In that we can identify the porosity, the voids, poor penetration, undercutting, and cracks. Here are some applications of non-destructive testing. You can use the non-destructive testing in aerospace and aviation for quality control and manufacturing, for ensuring the safety in the nuclear industry, also for the driving reliability in the automotive sector and the construction and infrastructure, also for the power generation and railways. Some challenges can also faced during the performing non-destructive testing, that are components needing to be cleaned before and after the inspection. Sensitivity of inspection can sometimes be affected by the finish of a component, and sometimes there might be a lack of depth sizing, and on some time non-destructive methods only relatively non-porous surfaces can be inspected. Some test methods require the electricity, and some tests are only effective on material that are conductive. Now let's start with the main topic of this presentation, recent developments in non-destructive testing for aerospace composites. The aerospace community is increasingly using composites in aircraft and space vehicles such as the Boeing 787 and NASA's composite crew module. As these structures become the larger and more complex, non-destructive evaluation techniques are needed to quantify and fully characterize damage. This is particularly important for carbon fiber reinforced polymer CFRP composite components, as it allows for the accurate life predictions. Acquiring quantitative NDE damage characterization for aerospace composite is challenging due to the size of the structure, complexity of damage types, and complex geometries of composite components. NASA's Non-Destructive Evaluation Sciences branch is investigating the various methods and using simulation tools for the optimization. Flash infrared thermography. So the flash infrared thermography is widely used rapid inspection technology for composite structures. The system from thermal wave imaging that is used by NESP, which features a flash hood with a 640x512 element FLIR SC6000 infrared camera and two 4800 joule xenon photographic flash tubes. The flash produces an energy density of 7.15 joules per square centimeter at the mouth of the hood, providing uniformly illumination across an area of 24.8 cm into 32.7 cm. The initial temperature increase of the inspection surface is less than 10 degrees Celsius. The system is connected to a base station which houses the system computer and power sources for the various components. Thermographic inspection is accomplished by placing the hood on the section of material to be inspected. Thermographic images of the specimen are captured by the using infrared camera for predetermined amount of time and stored in the computer for further analysis. The total inspection time per location is approximately 45 seconds, and the principal component analysis, that is PCA, with model derived eigenvectors reduce the processing time per data set to less than 1 second, which is less than the time required to move the camera and hood to the next inspection location. We can also see the figures. The figure number 1 is the photograph of the flash thermograph system. Figure 2 is the system configured for large area inspection of a composite test article. And the third figure is the image showing PCA processed thermal results for a portion of joint number 2 from the inner mold line. Second one is large area ultrasonics. The ultrasound is a valuable technology for non-destructive inspection of aerospace structures, but it can be problematic when surface deviate from the shape of solid coupling device. NASA has chosen to implement a captive water column coupling approach for a large area and high-speed applications. This method uses a watertight probe housing with a flexible membranes to capture water and mechanically scan the inspection surface. The scanning system allows for the automated inspections of a large specimens with scanning speeds up to 2 meter per second and full waveform capture every 0.25 mm. The total acquisition time for the captive water column ultrasonic inspection was approximately 45 minutes per site. First figure is of a photograph of a single element transducer with a captive water column used for a large area and high speed ultrasound. The second figure is of the ultrasonic C-scan result from the inspection of a large honeycomb sandwich composite specimen with an inset showing a skin to core delamination. Computational non-destructive evaluation. The simulation tool can be used to develop and optimize the damage characterization techniques for the composites and enabling the prediction of the inspectability of advanced composite components during the design stage. These tools can be used to simulate complex damage in a composite material such as a 26-ply quasi-isotropic IM7 8552 composite laminate coupon. The damage growth setup was fabricated at NASA, and the interaction of the guided ultrasonic wave with the delamination damage was modeled using 3D anisotropic elastodynamic finite integration technique EFIT software. The simulation results have led to an approach for the detection of hidden multilayer delaminations. These simulation tools can also be used to develop a new rapid quantitative method to analyze ND data such as PCA. PCA has been extensively used for the reduction of flash infrared thermography data, but it is also computational intensity and potential issues with the large defects are being addressed. An alternative method of PCA is being pursued where a fixed set of eigenvectors is generated from the analytical model of the thermal response of the material under examination. This method can increase the processing speed and eliminate issues arising from the presence of large defects. The first figure is the micro-CT result showing the complex nature of the impact damage in a composite specimen, and the figure B is the simulation of guided ultrasonic wave in the presence of complex delamination damage. Now let's see the conclusion of this study. The study reviews the recent non-destructive evaluation, inspection, research and simulation tool development for the aerospace composites. It discusses the technologies for rapid, large area inspection of complex composite structures, including realistic simulation tools for non-destructive testing and model-based data analysis. Other techniques explored include fiber optic, wireless surface acoustic wave, and acoustic emission sensors for structural health monitoring, ED current inspection, and terahertz and microwave inspection. The study also explores the combining data from multiple non-destructive evaluation techniques for better understanding. Thank you.